Welcome students to lecture 7 on the chapter wave optics. In last lecture, that is lecture 6, we tried to derive an expression for fringe width of the interference pattern produced using Young's double slit experiment. We also tried to understand how the fringe width depends on the wavelength of the light used, lambda, the distance between the plane of slits and the screen, capital D, and the distance between the two slits, that is small d. So till last session, we discussed the phenomenon called interference. In this lecture, we will discuss the next phenomenon, that is diffraction. Fundamentally, if you see the diagram here, more or less it appears very same as interference pattern, but there is a very significant difference, and what that is. So there in interference we had two slits. Now here we don't have two slits, we only have one slit. But even though we have one slit, the pattern that we are getting when the plane wavefront is incident on the slit is somewhat very same with that of the interference pattern or interference superposition. So what is the basic principle of whether it is interference or diffraction? It is the superposition of light waves. In interference, the superposition of light waves used to happen due to the waves from two different sources, whereas in diffraction, the waves which are getting superposed are of the same source. When the light is of the same source, how can it superpose when it is a plane wavefront in nature? Now try to understand, once the plane wavefront interacts with the slit or falls on the slit, the light bends at the edges of the obstacle. It bends at the edges of the slit, and once it bends, then it can move at various angles, and when it tries to move in various angles, it superposes with the wave coming from some other part of the wavefront. Now here the Huygens Principle is very important. Now let me state it once again. Huygens Principle says that each and every point on the wavefront acts as the source of secondary wavelet. So therefore, when plane wavefront falls on the slit, each and every point on the slit acts as a source of secondary disturbance, and this secondary disturbance tends to travel in all the possible directions. So due to which the superposition of waves happens and we get the diffraction phenomenon. How do we define this diffraction phenomenon? So diffraction phenomenon can be defined as when a wave is obstructed by an obstacle, the ray bends around the corner and enters into the geometrical shadow. So this phenomenon is known as diffraction. The waves, when they fall on the obstacle, it bends. So in the diagram that we saw, the slit was the obstacle and the light waves bent at the edges of the slit. We can think of another obstacle. Say if I make a light ray to fall on a sharp tip of a pin, the rays bend to form the diffraction pattern on the screen, and this is practically easy to get the diffraction pattern. You can try this at home, make use of a laser and fix the laser at some point and arrange a pin such that its tip should come in the direction of the light beam, and try to make the whole setup in a dark room, and if you keep a screen at certain distance, you will definitely get the diffraction pattern. So a pin and a slit both can act as an obstacle to give the diffraction phenomenon. Now let us discuss types of diffraction. So we have two types of diffraction. Among that, first one is Fraunhofer diffraction. What do we mean by Fraunhofer diffraction? The Fraunhofer diffraction is the one in which the plane wavefront is incident on the slit, and after diffraction the plane wavefront moves from the slit. So what do we mean by plane wavefront? A plane wavefront is obtained when the source is at infinite distance. Hence, the Fraunhofer diffraction is said to be the one in which the source and the screen are effectively at infinite distance from the slit. Now, if you see the diagram, we are using a convex lens. Now, why do we use this convex lens? Now, we say that effectively the screen is at infinity, but practically we need the screen to be placed at finite distance. So, to get the diffraction pattern on the finite screen, we make use of lens so that we can converge the rays. The second type of diffraction is called Frontal diffraction, in which the source and the screen are said to be at finite distance. Now, if you see, the nature of the wavefront that are incident on the slit is due to a point source, so hence it is spherical in nature. And since it is a slit, the wavefronts that move out of the slit that gets diffracted are cylindrical in nature, and the screen being at the finite distance. So since the screen is at finite distance, we need not use the lens. So frontal diffraction is the one in which the source and the screen are effectively at finite distance from the slit. Now let us discuss the diffraction by single slit. So this is a very important concept. So I request you to have patience and go through the content. Now we have a diagram here in which the light from the source S is falling on the slit, where L and N are the edges of the slit, end points of the slit. Now if the incident wavefront, if the incident rays had to travel straight, they would have gone straight to point C. And since the waves undergo bending as per the definition of diffraction is concerned, assume that after bending they make an angle of theta, and they move to the point P. If the waves bend, then assume that they make an angle theta to move to an arbitrary point P, where P is some point. Now try to understand. So A be the width of the slit. So we consider a single slit of width A on which the plane wavefront parallel to the slit are incident. The path difference between the two edges of the slit at point P is, now path difference from the two edges. Which are the two edges? The one is N, second one is L. So therefore the path difference between the two edges of the slit at point P is, it is given as NP minus LP is equal to NQ, which is equal to A into sine theta, which is equal to A theta. Now why A theta? Where theta can be assumed to be very, very small. I suggest you to see this diagram. Now in this diagram, point P is considered to be C. That means we assume that the waves have not bent. Okay, they have not bent, they are moving along the direction towards C. So if the waves, if they move towards C, then the C will be having the maximum intensity. So hence C is called central maximum. So let us try to understand what it means. So when the light waves moves towards C, then theta is equal to 0. The angle by which the light waves have bent is equal to 0. So when theta is equal to 0, path difference of the rays is going to be 0, because path difference A theta is equal to 0. Since theta is equal to 0, A theta will be equal to 0. When path difference is equal to 0, the waves that come from each and every point on the line Ln will be in phase. So when they are in phase, the crest reaches point C from L, crest from N comes. So therefore they are in phase. So crest from M1, crest from M2, both of them superpose at point C. So therefore every wave that comes from each and every point on Ln are in phase. So therefore, we get the maximum intensity at point C, and then this point C will be called as central maximum. So point C is the central maximum because we get the maximum intensity, and we get maximum intensity because the path difference is equal to 0. Now why path difference is equal to 0? Because the angle theta is equal to 0. The angle between the waves with respect to the horizontal is equal to 0. Now what if the angle is not 0? If the angle is not 0, then we have two kinds of possibilities. One, the point that we are going to consider may get a bright fringe or we may get a dark fringe, and it purely depends on the value theta. So what the path difference is going to be. Now let us try to understand that. So after central maximum, what we have is, now let us consider again the path difference between the two edges of the slit at point P be NP minus LP, which is equal to NQ, which is equal to A sin theta. For small angle theta, sin theta tends to be equal to theta, so therefore it is equal to A theta. Now see this diagram. In this diagram, the waves are bent by certain angle theta. So when they have bent by certain angle theta, the path difference is not, the path difference is not 0. So now let us discuss the condition where we are going to get secondary minima. So what do we mean by secondary minima? It is a position where we are going to get the minimum or 0 intensity. Now at point P, let theta is equal to n lambda by A. We consider the path difference now to be equal to n lambda by A, where n is equal to plus or minus 1, plus or minus 2, plus or minus 3, and so on. If this is the condition, then we are going to get minima or 0 intensity at point P. Now let us try to find why so. Why we are going to get 0 intensity at point P. Now let us take an example. Let n is equal to 1. When n is equal to 1, we call it as first secondary minimum. So for first secondary minimum, n is equal to 1. When n is equal to 1, then theta is equal to lambda by A. If theta is equal to lambda by A, then path difference, which is A theta, will be equal to lambda. So path difference between the light that comes from L and n at point P will be equal to lambda. What we do is, we divide Ln, wavefront Ln, into two parts, Lm and Mn. Now for every point as m1 in Lm, consider m1 is a point in Lm. So for every point as m1 in Lm, there exists a point m2 in Mn such that the path difference at P from m1 and m2 is equal to lambda by 2. So if a light from m1 reaches P and another light wave from m2, if it reaches P, then the path difference between the waves from m1 and m2 will be equal to lambda by 2. Now why it is lambda by 2? Because they are the midpoints of Lm and Mn. And now, what do we mean by path difference lambda by 2? Path difference lambda by 2 means that at point P, if m is giving crest, m1 is giving crest, then m2 is giving trough. So they are cancelling the effect of each other at point P. So therefore what we find is, the contribution from m1 and m2 are 180 degree out of phase and cancel in the direction theta is equal to lambda by A. Now, as we have m1 and m2, every part of Lm cancels the light from part Mn at point P. So therefore the contribution of two halves of the slit Lm and Mn therefore cancel each other. So when they cancel the effect of each other, we are going to get the minima, that is 0 intensity. No light reaches at point P. Now let us try to understand this by taking the second secondary minimum. Now assume that for second secondary minimum, now let the value of n to be equal to 2. If n is equal to 2, then theta is equal to 2 lambda by A. So therefore the path difference A theta becomes 2 lambda. When path difference A theta becomes 2 lambda, then the same wavefront Ln now can be divided into 4 equal parts. Okay, can be divided into 4 equal parts. the contribution from two consecutive parts. Now try to understand. Now since it has been divided into 4 equal parts, the total path difference is 2 lambda. If I make 4 parts of 2 lambda, it will be, each part will be having the path difference of lambda by 2. So therefore the contribution of each two consecutive parts are 180 degree out of phase and cancels in the direction theta is equal to 2 lambda by a. So again what I am going to get at point P? At point P, I am again going to get the 0 intensity. Now let theta be such that at point P we are going to get the maxima, that is maximum intensity. So at point P, where theta is equal to n plus half into lambda by a, where n is equal to plus or minus 1, plus or minus 2, plus or minus 3 and so on, we get maxima. Now let us try to understand why we get maximum. Why don't we get dark band if the path difference theta is n plus half into lambda by a? Now for first secondary maximum, let us put n is equal to 1. When I put n is equal to 1, then theta becomes 3 times of lambda divided by 2a. And path difference at point P from L and N becomes a theta is equal to 3 lambda by 2. Now the wavefront Ln can be divided into 3 parts, each of path difference lambda by 2. When we have each of path difference lambda by 2, the contribution from each of the consecutive parts, so the contribution from 2 consecutive parts, that is one red and another yellow, as you see on the wavefront, are out of phase and cancels in the direction, whereas the rays from the third part reaches the screen. Third part is retained and reaches the screen. So therefore, even though the 2 consecutive parts have cancelled each other, the light from the third part reaches the point P to give the maxima. So that's what we have here. So since the light reaching the screen is 1/3 of the intensity at point P, so the light that reaches the screen is only 1/3 the intensity at point P. It is less than that at central maximum. At central maximum, the whole light used to reach. So therefore the intensity at that point, if it is I, then intensity at point P, since it is 1/3. Why 1/3? Because 2 parts of the wavefront have cancelled each other. Only 1/3 is reaching at point P. So therefore at central maximum, if we have intensity I at point P for first secondary maximum, we are going to get 1/3, I by 3 times of intensity. Now let us try to understand the same case for the second secondary. In second secondary maximum, let us put n is equal to 2. If I put n is equal to 2, then theta will be equal to 5 lambda by 2a. Then path difference becomes a theta is equal to 5 lambda by 2. So now we divide the whole wavefront into 5 equal parts. Okay, each of path difference lambda by 2. So contribution from each 2 consecutive parts are 180 degree out of phase and cancels in the direction, whereas the rays from 5th part reaches the screen. Only 1/5 of the light will reach the screen. So therefore the light reaching the screen for second secondary maximum position is 1/5. So hence it is less than central maximum as well as first secondary minimum. Try to understand, it is only 1/5. So similarly, if I go for third secondary minimum, I put n is equal to 3. Now I have to divide the whole wavefront Ln into 7 equal parts. So first cancels with second, third cancels with 4, 5 cancels with 6. Only 1/7 light will reach the point P, which is at an angle 7 lambda by 2a. So therefore its intensity will be still smaller. So thus the intensity of the secondary maxima decreases as n increases. So if you see this diagram, at central maximum we have highest intensity because the total light from the wavefront Ln used to reach. As we move on either side, we get 1/3 of intensity, then we get 1/5. If we still move away from the central maximum, we get 1/7, 1/9 and so on. So therefore, as n increases, the intensity of the secondary maxima goes on decreasing. Whereas between 2 secondary maxima, we get a dark band. We get a dark band, which is secondary minima. Okay. So therefore, to sum up, at the center we have central maximum, then we have on either side first secondary minima, then first secondary maxima, then second secondary minima, then second secondary maxima, then third secondary minima, and so on. So this was the diffraction phenomenon by single slit. Thank you.